Welcome! This is the seventh in my series of videos about understanding space weather. This one is about solar evolution. The Sun's evolution is akin to space climate, i.e. long-term space weather. The current stage of solar evolution affects the conditions here on Earth, so it's very important to us. The Sun is about 4.5 billion years old, so in evolutionary terms it is middle-aged. There is a zone around the Sun which makes life possible. It's called the Goldilocks zone. Any closer to the Sun than the Goldilocks zone and it's too hot, like Venus, for life to exist, or too far away, it'll be too cold for life to exist, like Mars. As the Sun evolves, it's warming up, and so the Goldilocks zone will be moving further away, and eventually the Earth will no longer be within that zone. So how long will we remain in the Goldilocks zone? This graph shows the evolution of some of the Sun's major parameters. The red curve shows the Sun's luminosity is increasing steadily. In about 1 billion years' time, the luminosity will have increased sufficiently that the Earth will have moved out of the Goldilocks zone and become uninhabitable. Let's go back in time and see how the Sun was formed. It started off as a gaseous nebula. That nebula became gravitationally unstable and started to collapse. As it did so, the density and temperature in the interior of the nebula started to increase and a pressure started to build up. So there's a war between the gas pressure and the forces of gravity. Now gas clouds are quite large, so different parts of the gas cloud are orbiting the center of the galaxy at different rates. That's equivalent to a spin, and as the gas cloud collapses, the cloud will spin faster and faster, rather like an ice skater pulling in her arms while doing a pirouette. So we have three different forces operating: gravity pulling the gas cloud together, and the pressure in the gas cloud and the centripetal force trying to pull it apart. Now if gravity wins, we end up with a protostar. If you examine the stars in our galaxy, you'll see they come in a wide variety of sizes, masses, colors and ages. If you plot the luminosity or brightness of the star against its color or spectral type, you get a diagram that looks rather like this, with the large hot stars at the top left and the small faint stars at the bottom right. There are a few outliers like the red giants and white dwarfs. We'll talk about those in a minute. Most stars lie along the diagonal, which is called the main sequence. Now the spectral type has been classified by a series of letters: O, B, A, F, G, K, M, R, N, S. And that seems a little bit obscure, but there's a good mnemonic to remember those. Oh, be a fine girl, kiss me right now, sweetheart. One of the main characteristics of a star that determines where it will appear on this diagram is its mass. Large, heavy stars tend to be brighter and hotter, so appear at the top left-hand part of this diagram, whereas small mass stars tend to be cooler and fainter and appear at the bottom right. Another characteristic that determines where they are on the main sequence is the age of the star. Shortly after they form, they evolve onto the main sequence, and then for a time they evolve along the main sequence, eventually either dropping off if they're smaller stars to become a white dwarf, or if they're larger stars, becoming red giants. The Sun is a fairly average star. In fact, it's actually classified as a dwarf star, and it's a G2 type star, which means its surface temperature is about 57 to 5800 degrees Kelvin. The other thing that's important here is the composition. Earlier in the universe, stars were mainly made of hydrogen and helium. They tend to be rather massive stars and short-lived and explode into supernova. When those supernova form, they form heavier elements. Those heavier elements are then distributed throughout the remaining nebulae, and when those collapse into new stars, they incorporate some of these heavier elements. And the more heavier elements are in a star, or the metallicity of the star, determines what the opacity of the star is and what the temperature of the star is. It's also an important indicator of the age of the star, because of course more heavier elements means that the material making the star has gone through more supernova explosions, and also the ability of that star to have planets. As a star forms, it tries to shed excess angular momentum, forming a disk of material around the star. gravitational collapse can then make that disk form planets orbiting the star. But there's a differentiation process going on here. As the star turns on, the lighter elements will tend to be pushed away by both light pressure and also by any stellar wind that is formed. The heavier elements will tend to remain in the inner part of the planetary system. So therefore you will tend to get rocky planets form in the interior of a stellar system and gaseous planets in the outer part. And you see that in our solar system with the 4 rocky planets, Mercury, Venus, Earth and Mars, in the inner solar system, and the gas giants, Jupiter, Saturn, Uranus and Neptune, in the outer part of the solar system. You can see the consequences of this process in the distribution of mass and angular momentum in the solar system. The Sun contains 99% of the mass of the solar system, whereas all the planets and other debris orbiting the Sun only 1% of the solar system. Yet there's only 3% of the angular momentum of the solar system invested in the Sun, where 97% of the angular momentum is invested in the planets. So let's take another look at the main sequence. This diagram, by the way, is called the Hertzsprung-Russell diagram after the scientists that develop it. So most of the stars, as I say, lay on this main sequence, with the supergiants and giants laying above it and the white dwarfs laying below it. The Sun is a pretty average star, laying in about the middle of the main sequence. It has a surface temperature of about 5700 degrees Kelvin, and the luminosities here are measured with respect to the Sun, so by definition it's going to be a luminosity of 1. But you can have stars that are 1,000,000 times more luminous or 10,000 times less luminous than the Sun. Where a star falls on the main sequence determines its general life expectancy. The large bright stars have relatively short lives of just a few million years, where the small faint stars can last billions of years. The Sun is sort of in the middle of all of this. It's a G2 star, and so its life expectancy is about 10 billion years, and we're about halfway through that period. Now, in the distant future, it's going to evolve off of the main sequence to become a red giant, and then eventually a white dwarf. So over its lifetime, the Sun is going to go through some major changes in size. This little yellow dot here at the bottom left is the Sun as we currently know it. When it becomes a red giant, it will grow to be a very large size indeed. Some even say it might go beyond the Earth's orbit. After that star novas, in about 9 to 10 billion years, it will become a white dwarf. So here is the size of the Sun as a white dwarf compared to the Sun now. And you can see it's tiny. And in fact, the white dwarf that the Sun will form will likely be about the same size as the Earth. So let's see what we've learned about the evolution of the Sun. The Sun started life as a collapsing gas cloud. It's taken 4.5 billion years to get to the current state of the Sun. The Sun has been gradually warming for about the last 3 or 4 billion years and will continue to do so. In about another billion years, the warmth of the Sun will have increased sufficiently that the Earth will move out of its Goldilocks zone and become uninhabitable. 4 billion years before the Sun evolves into a red giant and ends life as a fading white dwarf. In my next video, I'm going to return to the subject of the solar cycle, but this time concentrate on that 70-year period back in the 17th century when the Sun apparently produced very few sunspots, the so-called Maunder minimum.